All right. So welcome to our fifth lecture. Today we're going to talk about the decision tree. So the quick definition, the goal, like any other goal, the other algorithms that we've had, is to create a model that predicts the value of target variable. What we've been doing, we've used linear regression, logistic regression, to try to predict the value of the target variable. And in this case, our target variable is if the people survived or not. Now, the way decision trees are different is by they do this a little bit different, right? Linear regression did this differently. Logistic regression worked a little differently. Decision trees work by learning simple decision rules inferred from the data features. Okay, this inferred by the data features is almost exactly like what we've been doing with, again, linear regression, logistic regression, right? Linear regression, it just infers the parameters, or it learns the parameters from the prior data that was given to it. Decision trees, they're not learning the slopes, right? In the linear regression, we had y equals mx plus b, and the m was being learned, the b was being learned. Instead, decision trees learn simple rules, decision rules, and we'll see what that means. But the best way, I think, to explain this is through an illustration. And so this is a decision tree if we're going to play tennis or not. That's just the example. Okay, so it's the overall image is this tree-like structure. And if you're familiar with graphs, this is just a graph data structure. But let's first start off with this first top of the tree, or upside down tree. We have the outlook. Okay, what we want to decide if we're gonna play tennis or not. And again, this is a classification task. It's a 0 or a 1. Will we or will we not play tennis? And so just for this example, there's three different initial rules: sunny, overcast, rain. Let's look at this overcast. Basically, this is saying if it's overcast, then we're going to play tennis. Okay, let's look at the sunny. If it's sunny, we want to check the humidity. Okay, we want to check, is the humidity high? If it's sunny and the humidity is high, then we don't want to play tennis. If it's sunny and the humidity is normal, then we do want to play tennis. Okay, let's look at the rain. If it's raining, we want to look at the wind. If the wind is strong and it's raining, we don't want to play tennis. But if it's raining and the wind is weak, then we do want to play tennis. Now, what's cool about this is if you've done any sort of programming, these are just a bunch of if statements, right? If sunny, and then if it's sunny, it's just a nested if statement. If humidity is equal to high, then we don't play tennis. Or if the humidity is normal, we do play tennis. It's just a bunch of if statements. What becomes unfeasible and impractical is if a programmer sits down and tries to write out if statements for a bunch of things, right? That's sort of impractical. But what a decision tree does is it tries to come up with these if statements for us. It tries to learn the general rules that predict what the target variable should be. And using these different rules that it comes up with, the rules are just if statements. And determining the if statements determine, okay, let's say it's sunny and it's the high humidity, then we don't play tennis. And so the rules are learned. The variables in this case are sunny, humidity, overcast, rain, right? Or sorry, the variables here are the weather type and the type of humidity and wind. Those are the variables. And using the type of the value those variables are at, it determines if we should play tennis or not. And so this is generalized to what we want to do. To learn different rules to determine if the people survived or not. Now let's look at another example. This is of a regression task. again, regression was with the linear regression. That was a regression task. It's trying to predict a specific variable, right? We have some data right here, and it's trying to predict a specific value. For example, it's trying to predict 500, or it's trying to predict, let's say, $515, just as an example. But that's a regression task. Classification, I'll repeat this a lot, but classification is zeros or ones, or twos maybe. Different classes, did they survive or not? Whereas a regression task is a specific numeric value. Decision trees work for regression as well. And this is just a visualization. Let's say we have this data right here, and it follows this sort of, I guess it's sort of a quadratic function, but not really, but it's this curved distribution. What the decision tree tries to do is learn these rules to determine what the prediction should be. And so we can see here, like, this rule means something. Basically, this is going to be some value or some rule that determines what the prediction should be at. And again, this y-axis is the prediction. And we'll see what these rules actually look like, because this is probably the best way to learn this is through the code. And so the best way, again, I recommend Python with this, but we'll go through the R a little bit. So let's just start the R off. Again, I have my two, you have to be in the directory. I have my two files right here, my test and train. Now we're gonna first read in the data. And just to check if it read in correctly, we can see this is the first 5 of our data. Now we're going to use a library. This should be installed in R automatically. I don't think you should be able to download. You don't have to download it, but the library is called library, and then R part, and then you put that in parentheses. And then what we're going to do is fit, or you can call this whatever you want, is going to be equal to R part, parenthesis, the ds of survived, which is our y variable, and then the x variables that we want. And we'll do what we've been doing before: age, sex, the p class, and the number of siblings. And again, to add multiple variables, because we have multiple variables, you just do the plus sign. Next, we're going to do data is equal to df, which is what we've been doing before. And then what's different now, though, is we're going to set method equal to parentheses or quotes class, and run that. What method equals class does is it tells our part, this decision tree, that we're using it for a classification task. Remember, decision trees support both classification and regression. And so we need to tell it that we're using what we have here is a classification task. Next, you can do summary and fit, and you get this giant text. But you can see here that if we look at these parts right here, these are the rules that we were talking about. These are the rules that it learns. And so we look at node number 1, right? And then what it's doing, what node 1 is doing, is predicting 0, which means that they didn't survive. And the rules that it's corresponding to are right here. The P class, if the P class essentially is less than 2.5, and the age is less than 6.5, and the number of siblings is less than 0.5, then it's going to predict that they didn't survive, essentially. And this happens for all these different types of nodes. And these are all the rules that we have. These are the rules that it sort of learned. And the if statements that we didn't have to program, but it just sort of learned these on its own. All right, so we've never actually predicted anything with R, so we'll just do that now. And there's a question. When it sets the right or left, is that moving to left or right branch of the decision tree? Okay, where does it say? Let me see. Left sun, so like right here. I think so. I'll be honest, I'm not too sure above that. Maybe if we go to the first one. Is this what you're talking about, Ben? I'm not sure. After DFP class. Oh, to the right. Oh, okay. I think so. That would be a good. I'm not too sure, I'll be honest, but if it's going to the left, to the right, then yeah, those are basically, it would be basically branching off of the previous rules. So yeah, this is the first rule in this case. And then this is basically branching from the left to the right. So that would be a good guess. I'm not too sure, but I believe so, yeah. All right, so we'll predict using we just trained this decision tree inside our fit. And so let's use this fit to actually predict, or like to predict the score that we get pretty much. So we're gonna do pred, or whatever you want to call it, is equal to predict. And this is a general function. You can do this for anything. For linear regression, logistic regression, this is generalizable. But the next, inside this parenthesis, we put what we trained it. And so the model we assign, the decision tree that's stored it's called fit. And so we just do fit. And this is the decision tree that is going to be used to predict. Next, we put in our data frame. And then we put in the type, which is again class, because it's a classification task. All right. And let's actually see what we get. We see this, we get this giant text right here. But this is our prediction, right? It's predicting the first person died, the second person didn't die, and so on for all of our variables, for all of our people that we have. All right, let's see what score we get, what accuracy we get. And so we're going to set table, again, you can call it whatever, it's going to be, or let's call this something else. Let's call it just T is going to be equal to table parenthesis df of survived, comma, our prediction. And we print that out, we get this right here. What this is a table that shows us the accuracy of our model or our decision tree. Basically, this 0, 0, and this 494. What this is saying is our decision tree predicted that the people didn't survive versus the people that actually didn't survive. And so the decision tree predicted that 494 people didn't survive when they actually didn't survive, which is correct. This is saying that the decision tree predicted that the people did survive when they actually didn't survive. So that's an incorrect prediction. Same with this. The decision tree is predicting that they didn't survive, but they actually did survive. And so there's 98 incorrect guesses right there. And then in this last column right here, the decision tree is predicting that they did survive and they actually did survive, which is correct. And so we can actually calculate the accuracy from these two values right here, because these two values, it got correct. These values, it didn't get correct. And so the way to just calculate the accuracy is just doing sum of diag of the table, or of T, and then divide that by the sum of the table. And we get 0.82. What this is doing is diag of T gets the diagonal values. So we can actually print diag of T. And you can see we get 494 and 245. Then what sum is doing is just adding those values up. And we get 738. And then so what sum of t is doing is just adding the entire thing. So 891, which is a number of people that we had. And what we do is we divide the number that it got correct by the number of total people, and we get 0.82, which is the accuracy. Now, we should be skeptical of this accuracy, and I'll tell you why. We'll look at it in the Python part of it, why this accuracy is not really correct. But we'll get to the Python part, and I'll show you why we should be skeptical of that. All right. Now in the Python, again, using Colab, but this will work for whichever, if you're using the regular install or Anaconda. So we're going to import pandas again. Read in our CSV file. And again, remember to be in the same directory as your files, or if you're using Colab, you have to upload them. And just to check we imported it correctly, df of head, and it's correctly. All right. Now we're going to do the same thing we've done before. Then we're going to choose the number of the columns that we want. And so again, just for now, it's sort of an arbitrary choice, but we're just going to do the sex, the age, the class, and the number of siblings. But again, if you remember, age has some null values, and sex is in male and female. And so we need to convert that to 0 and 1 and fill in the null values of age. And this is just from the last two lectures, but df.loc, df of sex is equal to male, comma, sex, just so we can get that value, is going to be equal to 0. Same thing for the female. And that's going to be set to 1. And then the age has some null values. So we need to fill that in with the median, essentially. You can choose the mean, you can choose, there's different values you can choose, but just for now, we'll just do the median. df of age dot fill NA, df of age dot median. And that cleans our code for us, or cleans the values that we have. All right, now we're going to set our x variable. This is the x-axis. The variables that we're predicting is going to be equal to the df of the columns. The columns, remember, we chose right here. And the y is going to be equal to df of survived. All right, now comes our decision tree part. What we're going to do is from sklearn, import tree. And then we're going to do the, we'll just call it, let's call it CLS for classification. CLS is going to be equal to tree dot decision tree classifier. I'm not sure if I spelled that right, but yeah, I spelled that right. All right, decision tree classifier is the class we're using to train our decision tree. If we're using a regression task, this would be decision tree regression. And then what we're going to do is cls.fit x and y. Very similar to what we've done before. And we get this. All right, now we want to see what our tree looks like. We can actually visualize it. What we're going to do is tree dot plot underscore tree, and then we're going to input this CLS. And we get this, ignore this part. but we have to wait a little bit. It takes a while. And we get this graph right here. This is our decision tree. It's extremely hard to read, like almost impossible to read because the font is so small, but it's our decision tree. We start off over here, and then we go to these two different types of rules. And depending on what the rule is, it keeps going down until it gets to some prediction. Again, very hard to see. What we're gonna do to actually see the rules is we're gonna do from sklearn.tree import export underscore text. And then what we're gonna do is print export text of our decision tree, which is CLF. All right, this is a little bit more readable, but these are our rules right here. It's a huge text file, a text of, see, we have feature 0 is equal, if feature 0 is less than 0.5, then it goes on to feature 1. Instead of having feature 0, this is a little unreadable. So instead we'll do CLF comma feature names is going to be equal to our columns. When we run that, we can actually see instead of feature 0, feature 1. All right, so we have these are our rules. If sex is less than 0.5, it moves on to age being less than or equal to 6.5. And then moves on to being, so basically if the number of siblings is less than or equal to 2.5, and the age is less than or equal to 6.5, and the sex is less than or equal to 0.5, then it's predicting that they did survive. And you can go through and see all the predictions for all the different types of rules that there is. All right, so let's print our score. What accuracy that we get? We get CLF.score x comma y. 0.9. I'll be honest, I'm not too sure why we get such a big difference from our Python and R versions. I think it's just because some parameters are different from the Python version, but I'm not too sure why. But it's not too important because we'll see. We also can't trust this score. And I'll show you what I mean by that. So we would think 0.9 is a really good score. And it is, right? 0.9 is pretty good. The problem is the score that we got is from our training data set. And so this is something called overfitting. When our model, which is our decision tree in this case, does really good on the training data set. The training data set is this train.csv file. It did really good, right? 90% is really good. We'll see now, it does not do so good on the test.csv, and we'll actually do what we did last time, which is put that into Kaggle and let Kaggle judge what we get. So let's actually do pd.read underscore CSV our test.csv. And just to see we read it incorrectly, test.head. And we get all that. Next, we're going to have to do the same thing we did up here, right? We're going to have to change the male, female to 0 and 1 and fill in the age. And I'm just going to copy paste because to save a little time. But instead of being df, we have to change all of this to the test. And that's going to fill in all the null values and change the male and female to 0 and 1. Because we have to do exactly the same thing we did with our training data set. All right. Now we're going to set our x test equal to our test of columns. And all this is doing is getting the sex, the age, the p class, and the number of siblings of the test variable, the test data set. All right. And now we're going to predict. So we'll just do pred is equal to CLF dot predict x underscore test. And let's just print this out. We get our prediction. So the first person, it's predicting that they didn't die. The second person that they died. The third person that they didn't die, and so on. Now we're going to do the same thing we did last time, which is to convert this prediction into a CSV file, just so we could put it, feed it into Kaggle, just so it could judge what score we actually got. Because this is the thing with overfitting, and we'll see why we or how we overfit. But you always have to test on data it's never seen before, because that's the actual metric that tells you, did your model actually learn, or is it just memorizing data? And so again, just like last time, we'll just have a data set equal to pd.data frame. I'm just referring to my notes because there's no point in memorizing this. But list of zip of the test of passenger ID, and then dot to underscore list, comma, the prediction dot to list. And then we're going to have the columns equal to passenger ID, comma, survived. And that should be it. Just to look at what we just did, print dataset dot head, and we see we're just taking the passenger ID and the survive and our prediction. Whatever we did right here, we're just making that into a CSV file. And then finally, to make this into an actual CSV file, to download it, we're going to do dataset.to underscore CSV, submission.csv, you can call that whatever you want, comma, index is equal to false. You run that and refresh this, we get a submission.csv right here. Let's download that, save it. And then let's go to Kaggle. All right. Let's go to the Titanic competition, and let's submit a prediction. Upload the CSV file. And then just describe. Okay, we'll just call this decision tree, and we make the submission. Okay, what score do we get? We got a 0.66. This is a little bit surprising, right? In the accuracy, the score that we got over here was a 0.9. But when Kaggle went to score us, we got a 0.6. And so this is overfitting, where our model did really good on the training data set, but did a little bit worse or poorly on the test data set. Basically, it didn't generalize well enough. And this is a problem that you'll find when you're doing your own machine learning, that you need to have a validation set, a separate data set where you don't train your model with, just so you can tell if your model actually learned anything useful. Because we can see that our training data set did better than our logistic regression, which got 0.75. But when we went to submit on data it's never seen before, it did pretty, like, not really bad, but it did pretty bad. And so that's it for decision trees. I hope this was helpful. And yeah, if you have any questions, let me know.